Good morning, geometry class. I am coming to you again from the elephant room to do another lesson on video, this time because we missed last Friday because of the ice storm. Decided this would be the easiest way to make that up, and so I hope this works for all of you. Of course, just call or email me if you have any questions, but what I'd like you to do is get out your week 22 notes, which is what we would have covered on Friday, and just follow along. I'm going to follow them pretty closely, and then your week 22 homework, so the practice homework and the graded homework will be due this coming Friday. So let's go ahead and get started on section 11.4. Starts with two words, circumscribed and inscribed. So I'm going to put those up here. All right, these two words essentially mean the exact same thing. They are describing a situation where you have a circle and you take a figure and you place the figure on the inside of the circle in such a way that all the vertices are on the circle itself. So, for example, if I was going to do this with a triangle, if I wanted to inscribe a triangle in the circle, I would make sure that each vertex was on the circle itself. And there's two ways of describing this. You can either say that the triangle is inscribed within the circle, and that's the terminology I use most often. But also you can say that the circle is circumscribed around the triangle. Again, interchangeable terms, they both mean the exact same thing. The important thing is that all the vertices of whichever figure you're inscribing are on the circle itself. So if I were to just draw a square here on the interior of the circle, obviously that'd not be an example of an inscribed square, as the vertices are nowhere near the circle itself. All right? Now obviously when you inscribe a figure in a circle, you create not only vertices on the circle, but for each piece of the figure, that piece of the figure represents a chord in the circle. Because remember, a chord travels through a circle and has its endpoints on the circle itself. And each chord creates intercepted arc. We talked about this some last week, that if you were to put a figure and inscribe it inside a circle, if that figure happens to be a figure that has congruent lengths, such as an equilateral triangle or a square, any sort of regular polygon, it would create not only equal segments for itself, but it would create congruent arcs all around the circle. And we're going to see that we can apply that same general principle in another way. And I'll show you how. All right. If you're following along on your notes, an inscribed polygon, that's the next term on your notes. You just want to put there that it's a polygon is inscribed on a circle if every vertex lies on the circle. And then we're going to move on to theorem 11.6. Write it in a little darker color. In a circle, two chords are congruent if equidistant from center. All right, so two chords, and we're creating chords on a circle. That's a line segment that travels through the circle and has its endpoints on the circle itself, are congruent if they are the same distance from the center. So how can you tell if they're the same distance or equidistant from the center? Well, on your homework this week, there'll be 3 ways to tell. And I'm going to draw all 3 different scenarios. All right, let's take 3 separate circles. Give them each a center. I'll use a different color. All right. The first way is, let's say I draw a short little segment here that connects to this chord. And then I draw another segment that connects to that chord. Okay? Now, what I want you to notice here is that these smaller segments that connect to the chords themselves are going to serve the purpose of showing you whether these chords are the same distance from the center or not. Think of them almost as like your measuring tool. Now, one way that you might know that they are equal in distance is if your diagram gives you tick marks. So you would have a tick mark through this and a tick mark through here. Obviously, it's saying that these 2 lengths are congruent. You would have to travel the same distance to get from center to this chord as you would have to travel to get from center to this chord. So, because both of these chords are equidistant from center, they're both the exact same distance from the center point, you can also conclude that this chord is indeed congruent to this one. And then taking it even one step further, you can conclude that the arcs created by those chords are also congruent to one another. So just that simple pair of tick marks really tells you a lot about the problem. All right, what if they don't use tick marks? What if instead of tick marks, they do something like this? Let's say you have, I'm going to retire this pink. It's not working too well for me. Can't see things very well. All right, let's say you have center and connected to 2 chords with maybe just a little bit of information about these places of intersection. Let's call them A, B, and C. So AC represents this line segment that basically travels through B. All right, notice again we have a similar situation where we have B to C represents the distance from center to the chord here on the right, and from B to A represents the distance from center to the chord on the left. So if we can prove somehow that these 2 lengths are equal, then we also prove that the 2 chords are equal as well as their 2 intercepted arcs. Okay, another clue that you might be given from your given information on a problem like this is point B is the midpoint of AC. So a statement like that will be kind of put up into your given information, and it'll be your job to notice it and then apply what it's saying. Of course, if AC has a midpoint, B, meaning B cuts that line segment perfectly in half, that of course means that AB is congruent to BC, and because of that, both those chords are equidistant from center, and not only do you have equal chords, but you have equal intercepted arcs. All right, and the last way that you'll be given that clue that your chords are equidistant is, let's say we draw 2 segments that connect to chords. They might simply just attach the same variable to both of those lengths. So if you're given the same variable or the same algebraic expression, even though you don't know exactly what that expression is representing, you know that if they assign the exact same variable or the exact same expression to both, there's your clue that they are congruent in length. And thus, all those other pieces are congruent as well. All right, so look for one of those 3 clues that you have equidistant chords in your problem. And let's apply that. Let's look at example 2. It is a figure like this. I draw the circle. It's called circle O because the point is at O. We have a couple chords running through the circle. One chord is RC and the other is ST. And then we have some pieces running through the middle, A and B. Okay, let's read. What is this problem asking us for? Point O is the midpoint of AB. All right, right away, that second scenario should be popping up in our head. Okay, they've mentioned a midpoint. They've said that point O is the midpoint of AB. Right away, that tells me this piece is congruent to this one. That means my 2 chords are equidistant from center. So before I've even started the problem, I know that RC is indeed congruent to ST. All right, so I've got that in my mind. Now, what exactly are they asking me to find? If CR, so the length of CR, that would be this chord right here, is represented by 2x minus 1, and ST, the chord on the right, is represented by x plus 10, find x. All right, now we've already established that the 2 chords are equal to each other because they're equidistant from center. So I can set up the 2 expressions in a really simple equation and use that to solve for x. And that's my objective in this particular problem. All right, so let's go through this. Right away, we notice we have variables on both sides of the equal sign, so we're going to subtract x from both sides to fix that. That would give us 2x minus x, which is, of course, just x, minus 1 equals 10. Add 1 to both sides, and we have an answer of x equals 11. And that's the end of that problem. All right, let's move on. All right, we learned last week that if you have a circle with center and you draw a specific type of chord that travels through the center of the circle and has its endpoints on the circle, that particular length is your diameter. And if you take just the length from center to one particular place on the circle, on this particular diameter, obviously I could draw one like this or one like this. That length is called the radius. So from here to here is the radius. All right, we learned this last week, that the radius and the diameter exist in a 2-to-1 ratio. So the diameter is equal to exactly twice the radius. All right, we know that already, but I wanted to review it because we use the 2 terms radius and diameter over and over and over again in this lesson. So it's important to keep them straight. Radius is half of the diameter. All right, so what we're going to learn to do is to calculate the circumference of a circle. Circumference of a circle. Now, the circumference means the distance around. How much length would it take to travel all the way around the circle? Now, we've studied lots of other figures in the past and used the term perimeter for distance around. We studied triangles and quadrilaterals and all those other types of polygons. When we get to circles, we just switch terminology and use the word circumference instead. The circumference. Now, I imagine when mathematicians were first trying to come up with a formula for how you determine the distance around a circle, they took the length of the diameter, which, remember, the diameter is that segment that goes through center and has its endpoints on the circle itself. They took the diameter, and I imagine they thought to themselves, wouldn't it be great if there's a direct relationship between the diameter and the distance around the circle? That would be really handy and make coming up with a formula pretty easy. So they took the length of the diameter and maybe started here at the top and stretched that length around the circle to see how many times it would go. And so it went once, and then it went twice. Now this is not drawn to scale, of course, but you know. And then it went 3 times, and then unfortunately there was just a little bit left over. All right, so I'm imagining they tried it again with a different size circle, maybe a much smaller circle. Took the length of the diameter and stretched that length around the circle, so to speak. And it went once, twice, 3 times, and then just a little bit left over. That little bit left over is the 0.14 and then a bunch of irrational numbers. Remember, an irrational number is a number that does not terminate and it doesn't repeat any type of pattern. It's one of those division problems from your nightmares that go on and on and on, and there's really, it will never end. And this particular number that represents the distance of the diameter around the circle shows that the diameter will go around the circle once, twice, 3 times, and then 0.14, and then several other numbers after that in a non-terminating, non-repeating type of way. That's pi, represented by this symbol right here. Remember, it's an irrational number that we often round off to 3.14. But just so you know, I'm going to add those little dots to show you that it really doesn't end. Now, if you're using a calculator to solve these problems, it will be really helpful to you to use the pi button on your calculator, because that will actually use the irrational number and it'll make your answers just a bit more precise. However, if you don't have a calculator at home that has the pi button on it, you can always just type in 3.14 for your rational approximation of pi, and that will work too. It might mean that at the 100th or 1000th place, your answer is 1 point off than the answer key, but I will of course recognize that it's probably just because you used 3.14 rather than the pi button, and that's totally fine. I'll know what you meant and I'll know if it's the right answer or not. All right, so that all goes to say, if you want to find the circumference or the distance around a circle using pi, here's the formula, and that's, you want to put the formula on your notes under theorem 11.7, and it is the circumference of a circle is equal to the diameter times pi. So the length of the diameter times 3.14, essentially. Now, what if the circle that you're given gives you the radius instead of the diameter? Well, hopefully that's a pretty easy fix for you to make, right? Because you know that the diameter is exactly half the length, or I'm sorry, the radius is exactly half the length of the diameter. So you multiply that radius by 2 and then multiply by pi. So that formula is simply 2 times the radius times pi. All right, so those two formulas mean exactly the same thing. One is simply using the diameter and the other is using the radius. All right. Let's look at a couple examples of using this pretty simple formula. We'll go through them quickly. Example number 1, the radius of a circle is 8 feet. Find the circumference of the circle to the nearest tenth. Now you'll notice this on your homework. They'll be pretty specific on several of the problems about how many decimal places to round it to. Either the tenth, hundredth, thousandth sometimes, or to the nearest unit. And what that means is just to round it up to the nearest whole number. All right, so let's look at the circle they gave us. We have a length of 8 feet for the radius. It specifically said the radius. Find the circumference. Now we know what we need to do is take the length of the radius times 2 and then multiply it by pi. You can pull your calculators out for this point, but basically what you'll be entering is 2 times 8 times pi. All in sequence. You don't have to hit equal or anything in between them. Just hit equal at the end. And then round that off to 1 decimal place, so 50.3. And then don't forget to include the unit as well, feet. All right, example number 2. The diameter of a plastic pipe is 5 centimeters. Find the circumference of the pipe to the nearest centimeter. All right, notice when it said to the nearest centimeter, that means round it off to the nearest whole number. So in this case, they've given us the diameter rather than the radius. So we get to use the slightly easier formula of simply the diameter times pi. And in this case, our diameter is 5. So you're going to take 5 times pi, hit equal, and you'll get a number that's a little bit, that has some decimal numbers to the right. And instead of using any of those decimal numbers, you're going to round up to the nearest centimeter, which would give you an answer of 16 centimeters, up to the nearest whole number. Okay. Page 2. Here's one of these odd little word problems. I'm going to read it out loud first. A circular garden has a radius of 20 feet. There is a path around the garden that is 3 feet wide. Jasmine stands on the inside edge of the path, and Hitesh, I'm not sure what sort of a name Hitesh is, but here he is, and he stands on the outside edge. They each walk around the garden exactly once while staying along the edge of the path. To the nearest foot, so to the nearest whole number, how much farther does Hitesh walk than Jasmine? Okay, let's draw a picture of this. We have a circular garden, and the circular garden has a radius of 20 feet. And then there's a path around the garden that is 3 feet wide. So there's basically a beautiful walking path around this garden. And at every point around that, it's 3 feet wide. Now, we have 2 characters. Jasmine, she's taking the inside track. She's not wanting as much exercise. She's going to basically stand right here. If we make this our starting point, she's going to walk around the garden following basically the inside circle. She's going to walk the circumference of the smaller circle. Hitesh, however, is an overachiever. He's going to stand here and walk the outside loop. So I'm sure you can all see this already, but what we really need to do is find the circumference of the small circle and subtract it from the circumference of the large circle, because what the problem asked us is how many more feet does Hitesh walk as opposed to Jasmine? All right, so we're going to take the circumference of the large and subtract it from the circumference of the small circle. That will give us our answer, and it does tell us to round it off to the nearest foot. So we'll round it off to the nearest whole number. All right, now we know that we can find the circumference of a circle, especially when they've given us the radius, by taking twice the length of the radius and multiplying it by pi. So there's our formula. Let's start with the circumference of the large circle. Well, because this large circle would essentially have a radius of 23 feet, because we take the 20 from the smaller and we'd have to add the little 3-foot edge to it. So we're going to take 23 as our radius times 2. Here I'm taking the radius and then multiplying it by 2. Remember, the order that you multiply is not important. And then multiply that by pi. And we're going to subtract from that the radius of the small circle, which is 20. You got to remember to multiply it by 2, and then times pi. All right, if you've got your calculator out, you're going to do all of that. You're basically going to get 144.44 for the large and 125.6 for the small. Subtract them, round it to the nearest whole number, 19 feet. So Hitesh, by walking the outside loop, is getting 19 feet more exercise than his friend Jasmine. All right, let's move on to section 11.6. All right, I want to introduce you to this phrase. It's on your notes, called "in terms of pi." Terms of pi. I really want to open up a bakery someday and call it "in terms of pi," and I think that would be really funny, and probably only a couple people would get the joke, but I would get the joke, and you guys would get the joke. But in terms of pi actually makes your problems easier. What it asks you to do is, instead of having to pull your calculator out, or your phone if you're using your phone, and actually type in pi, the pi button, and hit equal and get a big decimal number, if your problem is asking you to leave it in terms of pi, it means leave pi alone. Leave it in the answer as pi. Don't pull your calculator out and actually figure out the decimal answer to this problem. Kind of leave it alone. And I'll show you what I mean. Let's say you have a problem that says, find the circumference of a circle with a radius of, let's say, 10 inches. Find the circumference of that circle in terms of pi. All that means is you plug it into the formula just like always. So let's say I go, okay, well, I know that the circumference of the circle is found by taking the diameter times pi. And in this case, I have the radius, so I'm going to have to multiply that radius by 2 and then multiply it by pi. All right, simplify that just a bit, and that would come to 20 times pi. And then you just stop. You don't actually pull your calculator out and hit the buttons 20 times pi and equal. You stop right here and simply leave your answer as 20 pi. That's basically what they're asking you to do when your answer is in terms of pi. All right. So we always like it when they ask us to leave it in terms of pi because it just makes our problems one step easier. Okay. The next thing on your notes just talks about the exact value versus the rounded value. Now, the reason it's on your notes is I just wanted to bring up the point that whenever you're dealing with circles, you're nearly always dealing with pi. We know pi is an irrational number, and because of that, we're always having to round it. I would never ask you to write, 20 decimal numbers to the right of the decimal point. It would take, 10 years to do your homework, and that would be mean. So you're generally rounding off your answers. What I want you to look for on your homework is please be careful to pay attention to which to which decimal they want you to round your number. If it's to a tenth, round it off only one place. To a hundredth, round it off to 2. To a thousandths, obviously 3. And if they say round it to the nearest unit, obviously then you go to the whole number. That's just one thing to watch for on your homework, because it will affect your overall score. And also to include the units. Just little details that are really important on this lesson. All right, so now we're going to move on to Theorem 11.8, and that's the area of a circle. All right, so let's go back to the circle. We've already learned how to find the circumference. That would be the distance around the circle. We can find that by taking the diameter times pi, or 2 times the radius times pi. Remember, they mean the same thing. All right, how do we find the area? Remember, the area would be this two-dimensional measurement of covering the surface of that figure. We find that by taking the length of the radius, squaring it, and multiplying by pi. All right, so the formula for area of a circle is radius squared times pi. Now, again, another easy formula, right? The only difficult thing here is being careful to not mix it up with the formula for the circumference, because notice they look a little bit similar. On this one, especially when we use the formula in terms of the radius, you're multiplying the radius by 2 and then pi. On the formula for area, you are squaring that number. You're multiplying that number by itself. So obviously, your answers for area are going to be much larger than the answers you would get for circumference. So just be careful to remember to multiply by 2 when calculating circumference, and then remember to square it when finding the area. Okay, I'm doing that thing again where I start repeating myself over and over again, and I'll try to stop. All right, let's move on. Let's do just one example. All right, example 1. If circle S has a circumference of 16 times pi inches, notice they left that answer in terms of pi, find the area of the circle to the nearest hundredth. Okay, now this one is asking us to do just a little bit of detective work, because they weren't super nice to us and just gave us the radius, right? We need the radius in order to be able to calculate the area of a circle, because the formula for the area of a circle is radius squared times pi, right? They didn't just tell us the radius. They want us to be able to pull it out of this particular problem. What they did tell us is that the circumference of the circle is equal to 16 times pi. All right. Oh, I need to be able to pull the radius out of this expression. So what I'm going to do is use the formula for the circumference of a circle. I know that if I take 2 times the radius times pi, it will give me the circumference of the circle. And here I just do a little bit of easy elimination. The 2 pi's on both sides of the equal sign would cancel one another out, and that leaves me with 2 times the radius, I should really make this an equal sign, is equal to 16. Divide by 2, and the radius is equal to 8. All right, so they didn't just hand me the radius on a silver platter, but it was pretty easy to find it. The radius of my circle is 8. Now I can use that in the formula. So I'm going to take 8 squared times pi. Enter that into my calculator. And it does say on this particular problem to round to the nearest hundredth. So I'm going to round to 2 decimal places and get 200.96. Write that right here, 200.96. And we were in inches. And now that we're in area, we're going to make that inches squared, because now we're in squared units. All right. Now we have an interesting word problem. Before we do that word problem, though, go to page 3 of your notes, and I want you to just have the definitions for theoretical probability and experimental probability before we tackle the word problem, because it will make the word problem make a little more sense. Okay, theoretical probability. Oh, I gotta retire the green too. I'm having all kinds of problems. We're down to just purple. All right, theoretical and experimental. All right, if you're given a probability problem, and it could be anything. It could be, what's the probability if you go to the airport that the next 4 flights will be Southwest flights? Or what's the probability that you go to Taco Bell and they're all out of chalupas? Or what's the probability if you're playing a board game, you roll the dice and you roll a 4, right? It can be anything. Probability is just looking at what's the ratio between what you want to happen, so your desired outcome, over the total number of outcomes possible. All right, and there's 2 different ways to find that. Let's say I gave several of you math students a problem where I asked you to use experimental probability. Experimental probability means you physically have to do the action or go to the place or observe whatever phenomenon you're studying and record the data. Record, let's say you do a problem where the airport one that I just brought up. You go to the airport and you make a hypothesis as to how many flights coming in happen to be from Southwest. So what you do is you go out there with your notebook and your pencil, and you basically watch all the planes come in for the whole afternoon and record from which airline they came, and you come up with an experimental probability ratio. You count the entire number of flights that came in, and you set that below the number that happened to be Southwest, and that will give you your ratio or your percentage. So you have to physically do the work and record the data and come up with a ratio that way. Theoretical probability is, instead of having to physically do it, you use formulas, and you basically come up with mathematically, in theory, what should happen. So you take the formula for, let's say, if you're dealing with shapes, you can take the formula for the area of a square, and you can put it over the formula for the area of a circle if that square happens to be inscribed within the circle. And that would give you the theoretical probability of something landing on the square as opposed to the circle. Just an example. So theoretical uses formulas, experimental uses hands-on evidence. All right, so let's go back to the word problem, and this is going to ask us to use theoretical probability. And let's read it together. A pond has a radius of 10 meters. In the center of the pond is a square island with a side length of 5 meters. The seeds of a nearby maple tree float down randomly over the pond. What is the probability that a random seed will land in the water rather than on the island? Okay, so rather than sending you to this theoretical pond and making you count maple seeds that float over it, we're just going to come up with the theoretical probability of this happening based on the sizes of those shapes. So let's start with the pond. We have this big pond, and that pond has a radius of 10 meters. And then in the center of the pond is a square island. So let's draw a little square island here in the center. And each of the side lengths is 5 meters. Okay, here's our big tree over on the side, and it's got little maple leaf seeds floating from it. And what we're asked to do is find what's the probability that the seed will land in the water. So anywhere around the pond, or I'm sorry, around the island rather than on the island itself. All right, what we're gonna do again is take the probability ratio, which is your desired outcome, and put it over the total outcome. All right, using the formulas, we know that the total outcome would be the area of the entire pond. And we can find that pretty easily. The area of the entire pond would be to take the radius of the pond, the radius of the circular pond, which is 10, square it and multiply it by pi, because the area of a circle is radius squared times pi, right? All right, that will go on the bottom. And then on the top, what we'll need to do is take the area of the entire circle again, which we'll have already calculated here, and subtract from it the area of the square. Because we're asked what's the probability it's going to land in the water. So basically anywhere but the square. So we're going to take 10 squared times pi, again the area of the whole circle, and subtract the area of the square. Now notice the area of the square is going to be 5 squared, because that would essentially be 5 times 5, base times height. All right, 5 squared. All right, now this is pretty easy. What we're going to do is, this one, because it's in terms of 10, is one we can do in our head, because 10 squared is obviously 100. 100 times 3.14 is 314, and obviously there would be numbers to the right of the decimal as well, but for now let's just deal with whole numbers, since this is a real life type problem, or supposed to be. All right, so 314, we're going to use 314 for this value right here, because it's again 10 squared times pi. 314 minus, we know this is 25. Okay, so you've done all that. You'll take 314 minus 25, 289 over 314. All right, so we've determined that in probability terms, there is a 289 over 314 chance that those maple leaves will fall in the water rather than on the pond. Now, for a probability problem, it does help, at least in terms of making sense to our brain, to put that into a percentage form. Because who says stuff like that? Who says, there's a 289 out of 314 chance that this will happen, right? People's eyes will just kind of glaze over and they'll think you're crazy. It's better if you can say what percentage chance it will happen. And you find that percentage by multiplying the bottom number into the top. That will give you the decimal equivalent of this ratio. And then you move the decimal point over 2 places to turn it into a percentage. So 289 divided by 314 would come to 0.92, and I'm rounding. And then move the decimal point over 2 places, turns it into 92%. That makes a lot more sense, right? There's a 92% chance that the seed will randomly land on the water as opposed to the island. Okay, let's move on. It's the last thing we need to learn today. And that's how to find the area of a sector of a circle. Okay, so first of all, what is a sector? Well, let's take a circle. Last week we learned about central angles, right? A central angle has its vertex on the center of the circle and its end points on the circle itself. And we learned something really great about central angles, that the measure of the angle itself is exactly equal to the degree measure of intercepted arc. So if this happens to be a 100-degree angle, it has 100 degrees of intercepted arc, which is lovely, right? That makes these problems really easy. Now, what we're going to do is take a central angle and basically fill in all the space bounded by that central angle. And that would be a sector. A sector is contained within a central angle. If you want a little more of a definitive definition, a region of a circle bounded by a central angle and its corresponding arc. It's basically everything that falls inside of that central angle is a sector. What we're going to do is be able to find the area of that sector. All right, so here's what you'll do. In these types of problems, what you'll have to do is find the area of the entire circle, the area of the whole circle, and then you'll multiply it by a fraction that represents how big the sector is, how big that piece of the pie from the circle is. You'll find that particular fraction by the degree measure of the angle. So again, if I go back to this one and I say it was 100 degrees, a 100-degree central angle, that means you would have a 100-degree angle, and it would be 100 degrees of 360, because you know that the degree measure around an entire circle is 360 degrees. So the fraction that represents just this part of it, just this piece of the pie, is 100 over 360. All right, real quickly, why are you taking the whole circle times the fractional part? Sometimes I know some students look at me and think I'm making it more complicated than it has to be, but think about it, you do that all the time, just with kind of easier, more real life situations. For example, I like to use money as an example a lot. Let's say I come to school and I tell you that I have $100. I brought $100 to school. I don't know why I would bring $100 to school. I don't need to be buying $100 worth of pizza or snacks, but maybe it's registration time. I could definitely use it during registration. I brought $100, and then I tell you rather cryptically that somebody in the class has 1/10 of the amount of money that I have, and I want you to have to figure out how much they have. Well, you can do that in your head, right? Basically, you'd think, okay, if Mrs. Diff has $100, then I can multiply 100 by 1/10, which is essentially taking 100 and dividing it by 10, right? But 100 times 1/10 is equal to what? $10. So someone in the class has $10. We're following the exact same logic here. We took the whole and multiplied it by the fraction that represents how much somebody else has compared to mine, and we get the answer for the fractional part. You're doing the same thing here. You take the whole circle and multiply it by the fractional part. I'm starting to repeat myself again. I told you this in class. When you're just talking to a camera, you don't have students in front of you either nodding or giving you some sort of positive reinforcement. You start to wonder if you're making any sense, and so you just kind of start saying it over and over again. So I apologize for that. Let's do one of these problems, as I'm sure you've got it. I don't need to explain it anymore. Let's look at example number 4. Find the area of a 45-degree sector of a circle whose radius is 8 inches, and then round to the nearest hundredth. All right, so we know we're going to take the area of the whole circle times the fractional part, and that will give us our answer. All right, to make that a little more specific, we know we can find the area of a whole entire circle by taking radius squared times pi. And then to be a little more specific about this part, we know we'll take the measure of that central angle and put it over 360. And that fraction will tell us kind of what piece of the pie we have. All right, so it says to find the area of a 45-degree sector of a circle. So the 45-degree sector of the circle tells us that 45 degrees would need to go there as a central angle. So let me fill in what I know. It's going to be 45 over 360. And then if I keep reading, I can see that the radius of the circle is 8 inches. So I'm going to plug 8 in for radius, obviously. 8 squared times pi times 45 over 360. All right, now when you get to this part, you've filled in all the information that you need. You've put it in the correct spot. Here would be the time to pull your calculator out, and you can do all of these steps one right after another. Here's what you want to do. You're going to hit 8 and then the squared button. So you should be seeing 64, obviously, on your display, times pi. Then you're going to hit times 45 and then divide by 360 and then equal. You'll get a rather large number that keeps going and going, but you're going to round it off to 2 decimal places to get the answer 25.13 inches squared. And that is it. That really concludes the lesson for today. You'll be able to do all your homework. You'll do the chapter 11 review. And then in class, what we'll do is we'll jump into the next chapter, but we'll use whatever time we might have left over to answer any questions if you had them about this lesson and review for the test. I guess that's it. I'll see you all Friday. Thanks.